This video is solutions to this week 3 assignment. So essentially what's going on is you've got this electrically charged, massive, little tiny, in the problem statement, it's a ceramic ball, which doesn't really matter. But it's under the influence of an electric field. And electric field it really is a vector. And in your problem's case, the vector direction is towards the right. But we're going to study the situation where we have an electric field that's constant. That's scenario number 1. And also an electric field that varies in time. And that's scenario number 2. Right? So this is number 2, and this is number 1. Besides that, the details of the problem are similar between scenarios number 1 and 2. And the important sort of physics that you're getting are the acceleration, the velocity, and this other interesting thing, which is the energy associated with motion. It's called kinetic energy. The reason why this is full of physics and is also an assignment in your class is because acceleration is related to the net force as well as the inertia, the mass. And essentially what's happening in these two scenarios is the net force is going to be electric force due to a charge in an electric field, and the electric force is you take the charge Q and you simply multiply by the electric field. If the electric field is time dependent, you just keep track of the time dependence. It's a function of time instead of just some fixed vector value. But this is all divided by mass, right? So in here, to consider the physics of acceleration, this is really a Newton's second law problem. And we are doing Newton's second law with electric force. So it's a mix. So I think this is a cool problem because it mixes up electric force and inertia and kinematics, right? Acceleration and velocity are kinematics issues. So the velocity shows up in particular for our 2BC class, right? This is a calculus class. So you must have to do some calculus. And the calculus that we're going to do in this case is the fact that acceleration and velocity are related to each other via a derivative and an integral. In particular, the velocity might be a function of time. And if you have acceleration that's not 0, then you definitely have a time-dependent velocity. And it's equal to, loosely speaking, it's just the acceleration as a function of time times the really small interval of time, dt, right? It's a calculus move. It also comes up that we're also supposed to get expressions for x of t. Just in passing. But then, right, because you're in this physics class that, is getting you to use your math and your calculus, I also ask you to calculate the kinetic energy. And this, it turns out, is really easy if you already know an expression for the velocity as a function of time. You just have to take the mass of the object, divide it by 2, multiply by the function that is the velocity as a function of time, and you end up with an expression for the kinetic energy as a function of time. So let me go through the two scenarios. So scenario number 1, it has an electric field that is constant, and it's equal to 250, let me be more clear, so 250 newtons per coulomb, right? So the units are force per charge, so that if you was to multiply by a certain amount of charge, you're left over with a force, and that's how you use the electric field. In this case, scenario number 1, there is no time dependence for the electric field. We have this little massive ball, and the mass is 3.2 grams, which is pretty light, right? So newtons and coulombs are SI units, but the gram doesn't sort of necessarily fit with the newtons and coulombs in a very slick way. It turns out that the kilogram is the one that makes the most sense. So don't forget that 3.2 times 10 to the minus 3 kilograms is the mass of our object. And another detail is that the charge of our little ceramic ball is 4.0 nanocoulombs, right? And so in terms of scientific notation, this is 10 to the negative 9 coulombs. All right, so the idea is, right, so your problem asks you to draw a diagram. I think diagrams are very useful to keep you organized when you solve problems. So in the diagram, I want to include information about the electric field. I want to draw the little ball. I might keep track of direction. And if I'm feeling it, I might even include some indication that there is a force on this little ceramic ball. So what I'm going to do is indicate a rightward electric field with field lines that are parallel and spaced out equally, right, uniformly. This indicates a uniform electric field. And in the diagram, I might say that this is 250 newtons per coulomb. So that's a description of the field. And in this electric field is our little ceramic ball. And it's the 3.2 times 10 to the minus 3 kilograms. And it's the 4 times 10 to the minus 9 coulombs, right? So maybe I'll just, as a note, I'm going to indicate that it's a positive charge. And there is a force on this positive charge towards the right. So I'm going to just say those details. Another detail in this diagram, it's not necessary that you put it in there, but I'm just going to say at t equals to 0, there's two details given in the description of the problem. At t equals to 0, the location of the particle is called 0, and also it was released from rest. And so what this means is that x initial and v initial both have the value 0. Of course, the units are different, right? Because x is measured maybe in meters, and v naught is measured in, for example, meters per second. But this is a pretty good diagram for our scenario. The first thing that you're asked to calculate is the net force on the charge. So what is the net force on Q, right? That's one of the first questions that gets asked. And so the net force is only due to the electric field. So there's only one force that comprises the net force. So let me take away the question mark. The net force is just Q times E, where E is the electric field. So this is 4 times 10 to the minus 9 coulombs, and then 250 newtons per coulomb. And this is equal to, it turns out if you put this in your calculator, I'm going to put it as 1.0 micronewtons. You'll notice that in the data, there are two significant figures on all of your data, right? 4.0, 3.2, 250, right? The following zeros are just placeholders, so the 2 and the 5 are significant, but the 0 is not significant. Anyhow, yeah, so I'm just going to keep two significant figures, and there it is. And there's another detail that I'd like to keep track of. So I did calculate a net force just now, and the net force really is a vector, so I indicate vectors with little arrows above. So charge does not have a direction, but the electric field does, right? So when I calculate this net force, I need to keep track of the fact that this 250 newtons per coulomb is acting towards the right. So in the answer, I'm just going to put towards the right, right? You might have learned to use the unit vectors like I hat, right, to indicate positive x direction. But anyways, I'll just put a rightward arrow. So the next thing is, what is the acceleration? And is it constant or not, right? What's the acceleration? So in this case, the acceleration is going to be constant because there is no time dependence, right, to the force itself. So the acceleration is the net force divided by the inertia, divided by the mass. And the net force is, there is no time dependence, and also the mass, there is no time dependence. So in fact, our acceleration has no time dependence, right? So the acceleration is going to be a constant. So we're just ready for that. Another detail is the force definitely has a direction. It's towards the right. So that means the acceleration is also directed. It's directed towards the right. It's a vector. So this acceleration is pretty easy, right? So we'll just plug in the details. I've got 1.0 for the net force. I've got 1.0 micronewtons, but micro is 10 to the minus 6 newtons towards the right. And I have to divide by the mass, which is 3.2 times 10 to the minus 3 kilograms, right? Mass does not have a direction. Mass is not a vector. Mass is a scalar. And when you put this in your calculator and do the correct rounding, you're going to get to two significant figures. It's 3.1 times 10 to the minus 2 meters per second squared, right? Because these meters per second squared units, this acceleration, SI units of acceleration, is what the Newton per kilogram is, right? A Newton per kilogram is defined as the meter per second squared. In a sense, it defines what's meant by 1 Newton of force. So anyways, this is the answer, except for I forgot a detail, and the detail is the fact that there is a direction. The acceleration is towards the right. So those are the details. Okay, so the next question is what are v of t and x of t, right? So those are the next pieces. So v of t is related to a of t by an integral, but I'm going to be very pedantic at this point. When you integrate the acceleration, which might in general be a function of time, so I'm just going to put that. So when you do this, you have to, so we have this, kind of like experimental setup with data, and we have time t equal to 0 and then some variable time. So this is all to say that the way that I'm going to relate v of t and the integral of a of t dt is I'm going to first of all use a dummy variable. So this is a of t prime integrated against dt prime, right? Where t prime, this dummy variable, starts at the value 0 and goes to the variable value t. You may have seen this in your calculus class or your physics. Well, you wouldn't have seen it in 2B because, or 2A, because it's not calculus based, but in your calculus class, really this is what you're getting. And what this integral really is actually the change in the velocity. So it's the delta v from 0 up to t. So the change in the velocity is also known as v of t minus the velocity at 0, which is known as v naught, right? So that's all to say that really the integral should be this one that I just wrote. But I'm going to scroll up. If you recall, wrong. So if you recall, the initial velocity is 0. So this thing right here, I'm just going to put a 0 in for it. So, all right, so let's cut to the chase a bit. So, all right, so v of t, when, if you do the integral, right, a of t prime is actually independent of t prime. There is no time dependence. It's just this number here, 3.1 times 10 to the minus 2 meters per second squared towards the right. And so v of t is the integral from 0 to t of a, which is 3.1 times 10 to the minus 2 meters per second squared dt prime, right? And when you do this integral, you just get 3.1 times 10 to the minus 2 meters per second squared, and then t prime, which you have to evaluate from 0 up to t. And that evaluation is very simple. It's 3.1 times 10 to the minus 2 meters per second squared t, like this. And it's actually towards the right. So let me include the vector direction. So the velocity as a function of time is this expression right here. And if you look at the units, I've got acceleration units, but acceleration times time units is distance per time, which is velocity units, right? Can you see that meter per second squared times time gives us the correct units, right? So this is the expression for the velocity as a function of time. So similar to this construction here, we can also get x of t. So x of t minus the initial x is equal to the integral from 0 up to t, v of t prime, dt prime, right? Using this dummy variable notation. V of t looks like the expression we just got. So if you, and if you remember x naught equals to 0, right? At t equals to 0, we're setting the location value equal to 0. So x naught equals 0. And so what you end up getting when you finish this integral is the following expression: x of t equals, well, actually, let me be a little bit deliberate about this. So it's the integral from 0 to t. So v of t prime is 3.1 times 10 to the minus 2 meters per second squared. So there is the t right here, right? So it's multiplying t already, so that's t prime, and then dt prime. So if the integral is going to become 3.1 times 10 to the minus 2 t prime squared over 2, right? That's the integration, and you have to evaluate at the bounds from 0 to t. And so what you get is 3.1 times 10 to the minus 2 divided by 2 t squared, like this. And the units, I'm sorry, I forgot the units, meters per second squared, meters per second squared. And when all is said and done, 3.1 divided by 2 is about 1.6 with rounding. So 1.6 times 10 to the minus 2 meters per second squared, t squared, right? And this is x of t, like this. So if you check the units again, t squared, which is some amount of time squared, times meters per second squared could give distance, right? X of t is distance. All right. So yeah, so this is the answer for x of t right here. And the units work out. Oops, let me not. Yep. Okay. So the last sort of task in this scenario is to get the kinetic energy as a function of time. So the kinetic energy is just 1/2 mv squared But in our case, the velocity itself is time dependent. And so all you got to do is 1/2 3.2 times 10 to the minus 3 kilograms, right? That's the mass. And then you multiply by the expression for v of t, and then you square it. So here is v of t, 3.1 times 10 to the minus 2. So 3.1 times 10 to the minus 2 meters per second squared times time. But we have to square all of those v of t details, right? And so when you square this, you get, so 1/2 of 3.2 is 1.6 times 10 to the minus 3 kilograms, right? And then 3.1 gets squared. The 10 to the minus 2 gets squared. The meters per second squared gets squared, and the t gets squared, right? Everything gets squared. And when all the dust settles and you finish running your calculator and you multiply all these details together, you get about 1.5 times 10 to the minus 6, and then you're going to get kilograms, meters squared per second squared, and then t squared over seconds squared. You should make sure that you can do this transition, right? Especially, in particular, the units. So if you look at this thing that sits in front right here, that's actually joules, right? So that thing right there is joules. And then you're multiplying t squared over s squared, but the s is a time. So time squared over time squared is this last piece here actually doesn't have any units. So overall, this thing we are calculating as energy just is going to have units of joules. But if you clean it up just a little bit extra, you're going to get 1.5. And this 10 to the minus 6 is called micro, right? So this is 1.5 microjoules per second squared times t squared. And this is the kinetic energy as a function of time, like this, to two significant figures, right? Okay, great. So that's the end of scenario number 1. Scenario number 2 is just only slightly more complicated because the electric field is not constant in time. It actually depends on time. And if you go and you look at the expression for the electric field as a function of time, so let me put electric field as a function of time, it's equal to 2,000 newtons per coulomb second times time, right? Newtons per coulomb second times time. Let me clean up the units a little bit and make them a little bit more clear about where things sit. Oops. So it's newtons per coulomb second times time. And actually, I'm forgetting something. It's towards the right, right? The vector electric field is towards the right. So what I'm going to do in this case is I'm going to just list out the answers. And if you have trouble getting these answers because you're having trouble doing the integration, why don't you write me a note? But these solutions can serve as a set of goalposts. And if you're still having trouble getting to the goalposts, then you can write me a note and I'll help you individually. So essentially, what you want to do, or what the assignment asks you to do, is determine the acceleration as a function of time. That's the first step, and you get that from Newton's second law. And the expression that you should get to is 2.5 times 10 to the minus 3 meters per second cubed times t. And it is towards the right because the electric field is towards the right. So the particle is going to accelerate towards the right. And you can see that the units are going to work out because time times meters per second cubed has dimensions of distance per time squared, which is what acceleration is. Acceleration is distance per time squared. Okay, so then the next detail that you are requested to get, or that you have to get in order to write down the kinetic energy, is an expression for v of t. And v of t, you have to do the integral. And the expression that you're going to get to is 1.3 times 10 to the minus 3 meters per second cubed times time squared. And that's just from integrating the acceleration. So you'll get t goes to t squared divided by 2, and 2.5 divided by 2 is the 1.3, right? And if you look at the units are meters per time cubed, right? Distance per time cubed times time squared is overall distance per time, which is velocity units, right? So the calculus itself, the integration itself, is doing the right thing with the units. And then the last detail is to build up the kinetic energy as a function of time. And the kinetic energy as a function of time turns out to be 2.7 nanojoules per seconds to the fourth power times time to the fourth power. And this is an expression for the kinetic energy right here. By the way, if you also worked hard to integrate the velocity to get the position as a function of time, you should have gotten something like 0.43 times 10 to the minus 3 meters per seconds cubed times time cubed, like that. And that would be the position as a function of time. And you can see there that the units also work out. Okay, once again, let me know if you need help. Write me a message and I'll help you individually with your calculus. Okay.